Okay, folks, we're back. Again, not that time when these are recorded really matters, but just to place ourselves in time, it's now the end of July 2026. So it's been about a month actually since I've made any videos. So I'm a little out of practice. So I was on vacation and we did a elementary science camp at Shippensburg for 3rd through 5th graders. So that was a lot of fun. Also, I don't have any show to go along with this, but here's a quick tell. My wife and I did a bike vacation in upper New York State around the Niagara Falls region. Then we went to Ontario and we're up in Canada for a few days, and then came back, and then we're on Lake Erie and went on Prescott. But the thing I wanted to add, because it has relevance to what we just did in the opening video for part 3 of the book? Yeah, part 3, water chemistry, is I mentioned the documentary Poison Ground in Love Canal, New York. And actually my wife and I had a chance to go to Love Canal, which isn't a town. It's still officially Niagara Falls, New York, but it's a neighborhood. And I have to admit, it was a little bit infuriating to go visit this place. There's only one very sad looking monument to the tragedy of Love Canal, which if you watch the documentary or know anything about it, was really bad. And there's still over a 100-acre site in that area that's fenced off. That is a government Superfund site. Now we're actually going to talk about this, what Superfund means. That's not the official name of the federal legislation. It's a whole big long name, but it's been given the name Superfund. So there's a fenced off area, some housing developments, and even a retirement community bordering the fenced off area, and one sad little monument. So that was a little upsetting to me, as you might imagine. You can hear it in my voice. I just realized I had my phone in my pocket. Okay, so you've watched the intro video by now, which was a little long, and we're going to jump in. You're intelligent people, you can see this. We're going to jump right in and start doing some math. The first 2 sections here of chapter 10, you can read on your own, because it talks about concentration units, and it talks about the global supply of water, and I think I may put a couple of homework questions here to sort of update the knowledge about this, because the book was 2012, so maybe it's worth looking at some statistics about global supply of water as one of the homework problems. So you don't really need me to go through anything there. I want to stick to doing mainly quantitative kinds of things. So we're going to start with section 10.3 and jump in and start doing some math. So this first video, I'm going to do the solubility and the dissolved oxygen. So I guess this is just going to be sections 10.3 and 10.4 in this first video. And I'm a little out of practice, so maybe this one's going to be not as good because I was on a roll making videos before. Okay, so I'm not just going to use the exact examples from the book. So let me just get my notes here and we'll follow along with the slides as best we can. So you want the slides where it says Roman numeral 10, chapter 10, the chemistry of natural waters, and it lists a table there. And, well, what does that table mean? Okay, all right. So I'm going to make some references to that table as we go along here. So rather than talk about the natural waters, I'm going to talk about some pollutants to kind of get us started here. I believe I've used that acronym before, but it's been a month since I've done it. I can't remember exactly what I talked about. So compared to volatile organic chemicals. Now volatile means that it turns into a gas fairly easily, but remember what we're after here in this first part. We're after, if something's a gas in the atmosphere, even a natural thing like oxygen or carbon dioxide, is that some of it's going to go into the water. So there's an equilibrium between the gaseous state and the aqueous state, and we apply Henry's law in those circumstances. And Henry's law has a Henry's law constant. It's just an equilibrium constant that's set for a certain temperature. So rather than just do all the examples in the book, which we will do, of course, dissolved oxygen being the most important one, I thought we'd take a look at something else. So let's compare two VOCs, and these would not be the chemistry of natural waters, these would be pollutants, because you wouldn't want these too much. And you've probably heard of both of these, or I shouldn't say that, perhaps you've heard of both of these. So benzene has the chemical formula C6H6, and it is a 6-membered ring with alternating single and double bonds called conjugation. This is not an organic chemistry class, I'll tie it into some things you've known before. And you can look up the SDS sheet, the safety data sheet for this. This is a pretty toxic substance. Not that long ago, this was used pretty commonly as a solvent in the laboratory. People would even wash their hands with it. I even ran into some people that would redo furniture, like strip the varnish off of furniture, and they would use benzene. It's pretty dangerous stuff. So, anyway, and the Henry's law constant for this, I don't know exactly where I got this. I'm not sure this is in the book. So this is just something you would look up. It's 0.18 moles over liters times atmospheres, which, just to remind ourselves, moles per liter, please recall that that's the same thing as molarity. So that would be the same units as molarity per atmosphere. Nice. And then, so what's the chemistry that we're talking about here? So say you have some benzene, maybe it was an industrial accident, and there's some gaseous benzene, and it comes into contact with an aqueous system, a stream, a lake, what have you. So this is the chemistry that we're talking about. C6H6 as a gas. We could also do this as a liquid, but we're not talking about that right now. And we have water as our medium. And then we go to C6H6 aqueous. And please recall from Henry's law that we calculate the concentration of the aqueous species by taking the Henry's law constant times the partial pressure. That's merely Henry's law right there. Okay, so we want to calculate this. And in this case, what we're going to do, there's different ways to approach this math. So what I like to do is, what is the partial pressure? That's what we're going to calculate in this particular problem. We're going to do two of these. Hopefully I'll have room to do both of them on one whiteboard. Another thing you can look up is the concentration of something dissolved in water. That's called its solubility. So how much of it dissolves in water. Now this is expressed in terms of concentration units of molarity. When you look up solubility, and I did get this, I got a different number than the book, and I'm not sure why. So you can look this up in like the CRC Handbook of Chemistry and Physics, or look at a reputable source online. I might not necessarily trust Wikipedia. I would certainly verify that. But the solubility of benzene is 1.80 grams per liter. The book, I'm not sure where it is in the book, but the book used 1.0 grams per liter. I'm not really sure why. Okay, so what we can do is we can take something that's put into more sort of less abstract units, how many grams of benzene dissolve in a liter, and this is, I believe, 20 or 25 degrees Celsius. Well, for this, it doesn't really matter. Of course, this would be very different. If it was warm, it was a warmer temperature, it would be a higher solubility, lower temperature, lower solubility. So what we want to do is just do some unit conversion and convert this to molarity, which is not too difficult. So the liter part is right, so we just have to convert grams to moles. So basic stoichiometry. The molar mass of benzene is 78.12 grams per mole, and we end up getting, I'll just stick with sig figs here, 0.0230 is our molarity. Okay, now I think you can do this. We've done much more complicated math than this already, of course. So now we can solve this equation for the partial pressure of benzene under these conditions. So I'm just going to solve the equation. So the partial pressure Benzene would be, let's see, the concentration. I think I can just jump right to the data. 0.0230 molarity divided by the Henry's law constant, 0.18 molarity per atmosphere, and the partial pressure should have units of pressure, which it does, atmospheres, 0.13 atmospheres. Okay, so what is that saying? That's saying that under fairly reasonable temperature conditions, that the partial pressure of benzene is 0.13 atmospheres, so it's going to be somewhat in the atmosphere, it does somewhat dissolve, and this is just getting used to the math. Using an example other than what's in the book. Okay. Compare that to another one. Or you need to put this in your notes. Phenol would also be something you would not want to come into a lot of contact with. That's essentially benzene with an OH group called a hydroxyl group in organic chemistry. This is called an alcohol, and the OL ending, the suffix indicates that it is an alcohol, which is an OH ending. And the structure, which we don't really need, but is that right? Oops. So that's supposed to be a benzene ring, that's pathetic. And it doesn't matter where you put it. Okay, so conceptually, would you expect the solubility of phenol to be the aqueous solubility of phenol to be greater than, less than, or approximately the same as benzene? Just so we're not just doing math for no reason. So what would you think? Okay, so you can stop the video and think about it if you want to. This oxygen connected to the hydrogen is a very polar substrate. It's a very polar functional group, as they call it in organic chemistry. So this is a fairly polar molecule compared to this, which would be fairly non-polar. So when you put it in with water, like dissolves like, it dissolves a lot more. In fact, if you look up the solubility of phenol, it is 8.3 grams in 100 milliliters of water. So when I looked this up, I forget where I looked this up, I don't remember. They don't even give it per liter. So that's a lot more soluble, which makes sense conceptually because this is very polar. And the Henry's law constant is 2,820. I'm just going to go right to these units, molarity per atmosphere. So do the same thing. And you can stop the video here. So given this information, calculate the partial pressure of phenol compared to benzene. Conceptually, what would make sense? Would the vapor pressure, because that's what this is, it's the pressure of the vapor above the liquid, would that be, conceptually, should that be greater than benzene, less than benzene, or what? Now you might just go look at the numbers and say, well, okay, it's this. But again, we don't want to just do math. We want to make sure we understand why the math works based on the chemical structures. Okay, let's take a look at it, then we can explain it, and if you want to scratch down a few things in your notes, by now you realize I like compare and contrast questions because they make you compare things, and it's a little different level of understanding rather than just getting a number. Okay, so you can work on this if you want to, so you'll have to calculate the molar mass of phenol or look it up. So I'm just going to work the problem out. And you can stop the video and do it yourself if you want to. So we have to take the solubility first and convert that to a molarity, 8.3 grams per 100 milliliters. Okay, we have to go to liters, so a liter is 1,000 milliliters, right? Okay. And then the molar mass, using the periodic table, a mole of phenol is 94.113 grams. So in terms of molarity, it's 0.88 molarity. And I think you can finish this off. So if you solve the Henry's law constant, you'll get a partial pressure of phenol pretty small. Okay. Again, so justify this conceptually. Why would the vapor pressure, the partial pressure of phenol above the water be less than that of benzene based on the chemical structures, based on the interactions with water? Okay, so that's aqueous solubility. Transitioning now, we're going to go to dissolved oxygen, and this video will be kind of short, so I'm going to erase this and go right to the dissolved oxygen. And you can look ahead if you want to. This is pretty important stuff. The two things we want to balance here. Now this eraser is terrible. There's two things we want to balance here. Is the oxygen being dissolved in water, which is fine, but then also, is it an acidic environment or is it a basic environment? Because the redox chemistry is different in both of those cases. So I apologize, this is not a good erasing job of doing here. It's kind of a dirty thing. And I think I'm going to call an audible and stop the video here, get this cleaned up, and make the video for dissolved oxygen separately.